This webinar looks at Maple's Calculus Study Guide. Well, what is that? It's not a new textbook. It's an ebook designed to enhance any standard calculus of a single variables course. How does it do that? By examples. It's 460 some odd examples, resequence concepts and skills. So conceptual understanding comes before mastery of manipulative skills. And this is possible because Maple's syntax-free tools, live typeset math, palettes, tutors, assistants, task templates, control panel, embedded components, don't require learning syntax. Just point and click to conceptual understanding before emphasis on manipulations. So let's see how this works in practice. Let's take a quick look at the features of this guide. As we say, it's not a replacement for a calculus text. We assume that the user has a calculus text, but we try to provide insights that a paper text can't. And you can think of this as a manual for the syntax-free approach to using Maple in single variable calculus. A lot of sections gives us complete coverage of the calculus of a single variable, more than 460 examples. We use a document for each section written with typeset, Maple calls it 2D, live math, so the symbols are computable, and the paradigm is the Clickable Calculus paradigm. So we make use of palettes, embedded components, task templates, tutors, assistants, the context panel, and chiefly we separate math from Maple. In other words, we don't use Maple to convey a mathematical concept. If there's need of a mathematical concept, we present it mathematically the way you would find it in a book. And then we encapsulate that same construct in Maple. So we separate out the two so there's no confusion between why did we do it this way? Is it because Maple makes us do it that way? Or is that the way the math should go? And then the pedagogy is the resequencing of concepts and skills, which means we worry about developing the concept before we worry about developing manipulative skills. So let's take a glimpse at what we might accomplish today. Take a look at the table of contents of this work. This is what you would see if you installed a copy of this guide. The table of contents, there's a preface. There are 8 chapters and an appendix. You can see you have typical development of the calculus, limits, differentiation, application of differentiation, integration, some applications, then the techniques of integration, parts, partial fractions, trig substitution, then further applications of integration because now you have more tools, and then a unit on sequences and series. So what does a chapter look like? Well, a chapter has sections. Okay. A section has a summary of what should have been learned out of the calculus book, and it's called essentials. And so here you see what was considered essential in that first unit. It summarizes the key points, but the real action here is in the examples, where each example exposits an idea from that topic and captures that idea in both mathematical language and separately in the Maple. Then, in addition to taking a quick look at the table of contents, here are some examples that I would like to take you through so you can see how the material is developed. And there's one section down here that we might get a chance to look at. You can see how a particular section is laid out. For this first example, I'm going to pick the one that deals with what I think is the most difficult topic in calculus of a single variable, and that's the epsilon delta definition of a limit. Most books put this at the beginning of the course. I think it's a pretty steep hill to climb before the students can get to the mesa, the flat plains of the calculus, which I think is far easier than grappling with this concept. I always use an intuitive approach to limits. Then I did the limit laws, used them for limit of the difference quotient to get differentiation, limit of the Riemann sum to get integration. And I put this at the end of the course so as not to frighten the students or crush their spirit at the beginning with this most difficult of concepts to absorb. So let's take a look at what Maple has to offer here with regard to making this subject a bit more transparent. And I'm going to just take the limit of this quadratic as x goes to 3. The limit turns out to be 3. Let's see what Maple's got to say about this. Here's the definition of the function. You can see the recipe. Drag the equation f of x, or write the equation f of x equals, and pull this expression, pull the rule down, and use the context panel here. Let's put this there. Use the context panel to assign function. That takes care of all the machinery defining the function. Now, this is an animation. It's the typical animation of the epsilon band and the delta band. So move the slider, and you see the uniform epsilon band, and this is a delta band around 3. The secret to all of these calculations here is to realize that because this is a curve, you go up to here to where 3 hits the curve. The steepness here means that the gap from 3 to the green line is smaller than the gap from 3 to the red line. And the steeper this is, the smaller that right side would be. Okay? Because we want to find a region, a uniform region around 3, delta to the left and delta to the right. So if you merely knew these intersection points, that would not be a uniform band. So you have to make these estimates. And it's making those estimates that's so very hard. Attacking this problem by trying to solve inequalities is hard. So let's just find these 2 intersection points to begin with. And I will find them in terms of this gap, which I call delta L, and this gap to the right, which I call delta R. So there will be 2 solutions because this straight line, the red line and the green line, intersects this parabola twice, right? And one of the solutions is going to be out here, and we have to pick the correct ones. So here is the correct delta L, and here is the correct delta R. We find those solutions by writing the appropriate equation, and we use the context panel as a solve option. You can solve with various strategies, and here we have obtained solutions for, and we want either delta L or delta R. Then we need to find the smaller of the 2. So we need to compare delta L and delta R. And from our reasoning up here in the animation, we can figure that it's going to be that delta R is the smaller. We want to show that delta R is the smaller. So one way to do that is to draw the graph of delta L and delta R, right? the graph of delta R appears to be below the graph of delta L. That's not definitive, it's suggestive. Another way is to look at the ratio delta L over delta R. If delta R is smaller than delta L, this ratio will be greater than 1. And we pursue that approach. So here's delta L over delta R. We did a simplify, just use the simplify in the context panel. We have this expression. Well, here's a graph of this expression. It would again appear that this expression, being greater than 1, says delta R is the smaller of these two gaps, two intervals, and it will be delta R, if it's indeed the smaller one, that we want to take for the delta given the epsilon. Well, let's take a look at this fraction analytically. Let's see if we can show analytically that it's greater than 1. So here's the fraction, and what we have to do, we have to rationalize the denominator. So here is the mathematics of rationalizing the denominator. You multiply through by the conjugate of the denominator. Follow through the algebra. This is an equality. It becomes an inequality when we put in something smaller. Right here, it's root of 9 plus 4 epsilon, taking epsilon as positive. So if we put a minus rather than a plus, this is going to be a smaller quantity. So the inequality goes this way. And then when you do the algebra, the numerator turns out to be 4 epsilon. You're dividing by 4 epsilon. So this ratio is indeed greater than 1. So what we want to do is take the delta to be this delta R, and the delta R is this expression here. The final part of a rigorous proof requires that you show if x minus 3 is less than delta, and we choose that to be delta R, that guarantees that the function value is within epsilon of 3. Here's how I did it. Took delta R and a multiple of it, t, where t runs from -1 to 1. Okay, that allows me to explore the interval delta R to the left, delta R to the right. Okay, so I'm looking at the function value at 3 plus t delta R, so I'm somewhere in that interval, and I'm comparing the function values to 3, and now the rest is some algebra and then some estimates. So here's the algebra. There's a term multiplying t squared and a term multiplying t. Apply the triangle inequality. So this is the term that has the t squared. This is the term that has t, but t is between, or absolute value of t is less than 1, so you can replace t squared with t and strengthen the inequality. Okay, so that will bring out absolute value of t to the right, and then if you do the arithmetic of what's in here, it turns out to be epsilon. So epsilon times a factor which is less than 1, you strengthen the inequality some more, and this expression is less than epsilon. Well, this is pretty tough stuff, but it is a process that can be reproduced for almost any example. You find the endpoints of the interval, then you find the smaller of the two deltas. Try that for the delta and use that somehow to prove that it works. It's tough sledding, and it's the reason why I found it's wisest to put this approach to the limit at the end of the course rather than at the beginning. This example deals with the differentiation rules, and here you can see that it'll take us over to look at one of the tutors. Up here it was visualization and supportive analysis, and you can see what the highlight of that example is. The example is to apply the rules of this table, differentiation rules, to get the derivative of this function. We can put this table away. By way of solution here, we want to initialize, so that means first bring in the Student Calculus 1 package. Okay, where does it live? It's part of a library. It's all part of Maple. It's just organizational structure. Tools, load package, and go down here to Student Calculus 1. Since it's already in place, if I click this single exclamation point, that will redo that computation. To get the function defined, select the statement f of x equals, hold down the control key, and move it to where you want it to go. I'm going to move it down here to show you. It's equivalent to a copy paste, but it takes less effort. Okay, so that's been redone. I can redo this one. So that redefines the function. So now we're ready to get started. What's a stepwise solution to this problem? Well, here's one way to organize a solution. Here are the rules. This is the effect of applying those rules. So, for example, a sum rule, which breaks things at the pluses and minuses. Derivative of a constant is 0. A constant multiple, here this 3 is taken out. Then two rules. Identity rule here, this is what Maple calls the identity. And the power rule is applied here. You do a little arithmetic, and you get this final result. Now let's see how Maple can generate this kind of a stepwise solution. Okay, so we make use of this differentiation operator, which is in this calculus palette. It's this operator right here. So this template, you click on it, and it ends up where you last were. Apply it to f of x. Use the tab key to move through the fields. You right click. You'll see down here in Student Calculus 1, you have these options. All solution steps. And Maple generates this annotated stepwise solution where you can see which rules got applied to get the various steps of the solution. Well, it'd be best if the student, the learner, had to implement these steps, and there's a way to do that too. We saw that in addition to all solution steps, you have the option, tell me what to do next, and maybe we'll respond with the appropriate rule that you apply next. Or you can ask for the list of rules, and then you select from that list of rules which rule to apply next. So not only will Maple just give you the answer, but Maple will allow you to work your way through to the answer step by step. In addition to access to these rules through the context panel, there is the differentiation methods tutor. So the tutors live up here. Tools, tutors, and here you see single variable calculus and a list of tutors, which are pop-up tools. You can see what it looks like in that image that I've captured and pasted in. Differentiation methods. There's one like this for limit methods, and then there's one like this for integration methods. Okay, so if I click this button here, the differentiation method tutor will pop up, and it's been programmed to have this function f of x in it. And then you have the buttons for applying the rules. You can either ask Maple for the next step. If you don't like that, you can back up. You can ask Maple for a rule that doesn't apply, like the quotient rule. And Maple will tell you, don't do that. And it will say, look, there's a plus in this thing. Doesn't that tell you something? So there's also the all steps. And when you're done, when you click close, you will get the annotated solution printed as if you had done the context panel all solution steps. So this is a different way to get at. Oh, let me show you one other thing about this. The understood rules. These are the rules, and you can tell Maple, I know this rule. Don't bother me to apply it. Just apply it yourself. So that's something that you can do with the tutor that you can't do with the access to the context panel. So there's room for both. This example is an application of differentiation, finding tangent and normal lines, and it will bring us to the use of a task template. The particular example has us look at the graph of this function, quadratic, and at a particular point x equals 2, obtain the equations of the tangent and normal lines and draw the graph of the function and these lines. Let's take a look at the solution that's provided. Well, there is a mathematical solution, a solution that one would read in a textbook to separate out the math from the Maple. So this is the math part, right? You need to know the derivative at the point in question. So that's x equals 2. So you have to compute the derivative. You evaluate the derivative at 2. You get 7. That'll be the slope of the tangent line. Its negative reciprocal will be the slope of the normal line. And this is the point slope form of each line here. This is then brought over to the graph. So you have in red is the graph of the curve, and you have the tangent line and the normal line. So this is what this example is getting at. So there's a task template. So what are the task templates? Tools, tasks, browse. So you have a table of contents here for the tools, for the task templates. So here in differential calculus under applications, you see you have a task template for a tangent line and one for a normal line. This is the task template. You insert it by clicking one of these insert buttons. Default content means you get the extra verbiage. Minimal content means you get enough to make the thing work. And I've got it embedded in here already. So this is the path to it. And here you place the function. Here you put the point at which you want the tangent line to be calculated. Click this button, you get the tangent line. And then you want to see the computational details. This is the derivative. This is the derivative evaluated at the given point. So that becomes the slope of the tangent line. This is the function value at this point, so that's the y coordinate, and then this is the point slope form of the line, and here's a picture. Similarly, there's a task template for the normal line. Showed you where that was. Here's the path to it. Works the same way. function, point of contact. Here's the normal line. Computational details. You need the derivative, slope, the y-coordinate, point-slope form of the normal line, and a graph. Of course, students should learn how to implement these calculations from first principles. So here is a way of doing that in Maple. We've seen how to define a function. You bring f of x equals in the rule. You go to the context panel and assign function. Now here, this notation, f prime at 2. That's the notation you see in the textbook for the derivative evaluated at 2. Maple understands exactly what that notation means. The prime I've taken from my favorites palette. It's this symbol here. You could use an apostrophe, but I don't quite like how an apostrophe looks, but it would work. Prime. Where did I get that prime symbol? In the punctuation palette, you'll find prime, double prime, triple prime, even a quadruple prime. You right-click, and it says Add to Favorites. So that's how I populated my favorites palette, so that I can access things that I use frequently more readily. So f prime at 2, that will evaluate to 7. And then this is the point slope form of the line. F at 2, that evaluates to 9, which is the appropriate number for the y-coordinate. And here you see the negative reciprocal, and you get the normal line. To draw the graph interactively, you need the rule, and you click on that rule, and you have access here. You can go to the plot builder right from here, or you can get it from here, plot builder. Okay? So when you select the plot builder, what happens is it's embedded in the worksheet, so it's part of the worksheet, and you can see which options it takes to draw the graph you want. The options here are the range. The default is minus 10 to 10, and you just want to look from, say, 1 to 3. So you put 1 to 3 here. And then you go to 2D options, and you get constrained scaling. So you would start out as unconstrained, but you want it to be constrained, so you get a 1-to-1 aspect ratio. Then to get the equation of the lines down onto this graph, what you do is you copy the rule. So you do a copy, Control C, and you come down here and you do a paste, and it adds the graph of that expression to the existing graph. You did it for the tangent line, you do it for the normal line, and you can construct this graph interactively. This example has us computing area between curves, and it will give us a chance to look at some animations. The particular problem has us calculate the area of the region R, which is bounded by the graph of these functions. 1 linear, 1 minus 3/2 x, and root of x. So visualize there's a little region up in here. Let's see how the solution goes. First of all, there's a mathematical solution where we explain the math independent of its implementation in Maple. But we make use of some of the tools of Maple. For example, this is an animation. Let's just use the slider here. This animation shows a vertical strip traversing the region. And notice that the region has been drawn in Maple, which is a benefit to the student who struggles with graphing. But right now there's graphing calculators and stuff around, so graphing isn't the problem it used to be. Okay, so this animation shows that when the vertical strip hits a certain spot right there, the bounds on the integration change. On the left, it's between the green and the black, and on the right, it's between the red and the black. And so this animation helps the student understand that a vertical strip for this region is not the most efficient. because it's going to require writing down two integrals. Well, one thing you have to do is you have to get the coordinates of this point A, because you have to know where the switchover occurs. Okay, so here's where the coordinates of the point A are given, and you can see that you have two integrals, green to black, red to black. Right, so x equals 0 to x equals the x coordinate of A in the first integral, and then x equals that x coordinate of A over here to 1 in the second integral. If the integral is done with horizontal strips, then it can be done with one integral. And this animation illustrates that. It shows a horizontal strip moving from the bottom of the region to the top of the region, and the left and right boundaries remain the green and red lines throughout. What you need to know, because this is a dy integral, you need to know the y coordinate of this point A, and you integrate from there to 1, but you have to express these bounds as functions of y. So a maple solution begins with data entry, and then we'll calculate the coordinates of that point A, the intersection point A. So this is the rule for G, and I have simply assigned it a name. I didn't make it a function. I just gave it the name G. Same with the square root here, which is the rule for the function h, and I just gave it the name h. I said G equaled h, and that gives me this equation. Right click, you get the context panel solve. I selected obtain solutions for x. There's what you get back for x. And I gave it the name ax. Well, I want to put ax into either f or g. But since it's not a function, I can't go f of ax or g of ax. I can't do that because it's not a function. So I make use of this evaluation template. It stands for the eval command. It lives up here in the expression palette. It's right there in the expression palette. You right click on it, add to favorites. That's where I got it from. So evaluate G at x equals ax. You get this number and give it the name ay. Now the integral by vertical strips, that's the one where you have to split the integral into two pieces. And I do the integral with this calculus palette template, definite integral. Okay? And I've got that template here in my favorites palette. That symbol, that integral symbol, is live. It computes what it represents, which is the meaning of live typeset math. Okay, so we saw in the math solution, you have to integrate from 0 to the x coordinate of the intersection, and you are integrating 1 minus g, that's black minus, what was that color? Green. Okay, and then here it's from, the second integral is from the x coordinate of the intersection to 1, and it's black minus red. Okay, you get this expression. You hit it with a simplify. Here, let's hit it with a simplify, and you pick the simplest simplify. You get this, and then you want to know what is that roughly, and it's, you can approximate it to 5, 10, 20 digits, and you get the same number that we had up there in the math solution. To integrate by horizontal strips, you have to express the left and right boundaries as x is a function of y. And so you need the inverse functions. Okay, and I've done it here by inspection. Okay, to do it in Maple, set y equals the expression for g, and you want to solve this for x. So you saw how to solve for x. You get this, and I gave it the name big G. Little g, big G. The other function is a square root, so its inverse is y squared. I just wrote y squared. You're integrating y squared minus g. That's the strip. It's a dy integral, so it's from the y coordinate to 1. You get this expression. It simplifies to this. It floats to this, which is the same as we see here. This example is volume by slicing, and it will enable us to do some visualization. The particular problem is to find, by slicing, the volume of the solid whose base is in the xy plane, and the base region is bounded by x-axis, curve y equals sine x, x equals pi over 2, and cross sections parallel to the YZ plane are equilateral triangles. Well, let's see what Maple's got to offer by way of help. So here's the mathematical solution, and it's got some figures drawn. This is what the solid looks like. This is an animation that shows, here, let's just have it run. It shows the equilateral triangles, which are the plane sections, traversing the solid. All right, let me stop that there. The computation of the area of one of these equilateral triangles is the next step in the agenda. The area of that equilateral triangle is given by this expression. Where did it come from? Well, you got two different ways to come up with it. Here's the equilateral triangle. This is the base. So its length is sine x. That means this edge is also sine x. You can use the formula 1/2 AB sine C, where this is one edge, this is the other edge, and this is the angle included. That's a 60-degree angle. That will give you this expression for the area. Or you can do it the hard way, do similar triangles and figure out what the height of this equilateral triangle is using 30, 60, 90 triangle. Either way, you end up with the expression for area. There it is. So you can use the definite integral template here. Definite integral template. You're integrating from 0 to pi over 2. It's a dx integral. You're basically integrating sine squared. There is the value that you obtain. So really all of the hard work has been done in the analysis. The Maple solution, after the drawing of the solid and that animation, we set up the integral that we see here, set it up in Maple, get this answer. However, you're integrating sine squared, which is one of the integrals that students are asked to master. You have to use a trig formula to replace sine squared. Okay, so we've shown how one can obtain stepwise solutions for differentiation problems, and the same thing applies here to integration problems. So I'm going to make sure that the Student Calculus 1 package is installed. Write the integral here. Okay. In Student Calculus 1, you have this option for integration, all solution steps, or you can go stepwise and you can ask Maple, well, tell me what the next thing to do is. Or you can look for the list of rules and you can apply the rules stepwise. Okay, so this is just a screenshot of what this student calculus 1 option in the context panel leads to. Okay, so there is also the integration methods tutor, like the differentiation methods tutor, and you have again this option of using understood rules, which you don't get if you use simply the context panel. This example has to do with the algebra of partial fractions. We get to see a mathematical solution, a task template, coded solution. In addition to the algebra of the partial fraction, there's the other part, there's the integration of the decomposed fraction. But in this example, we're just looking at the algebra of the partial fraction decomposition. So for this rational function that we've chosen, a mathematical solution independent of Maple shows the rational function set equal to its template fraction decomposition. I like to use the method where you multiply through by the common denominator here, or you get some cancellation, but you end up with an equation that you can assemble so that you match coefficients. So the coefficient of x on the right must be 7, which is the coefficient of x on the left. Same with the constant term. That gives you these two equations, which you solve for a and b. Turns out a and b are these numbers 2 and 5, or a1 and a2 rather, and you have the decomposition. There are other ways to do decomposition, but when I was in the classroom, this is what I taught, because this is the way I think about it, this is the way I would do it. Let's see what Maple's got to offer here. First of all, if you put the rational function in place and go to the context panel for conversions, you find convert to partial fractions. Variable is x. There's the answer. Now, another approach, more mathematical, is to treat the decomposition as an identity in x. In other words, calculate these two constants a1 and a2 that make this equality an identity in x. Okay, so if you set that up and you go to solve, you have the option solve it as an identity. Okay, now when you make that choice, there'll be this pop-up where you have to identify the independent variable and the names of the parameters, and Maple then solves and returns values for a1 and a2. There's also a task template for this. Now I've shown you where the task templates are. If you click this link, it'll take you to the help page for that task template. Explains how it works. Here is the task template already embedded. You put the rational function in here. This button factors the denominator. In this box, you write the template fractions of the decomposition. This button checks to see if these are the correct template fractions and tells you if they're correct. If they're not, there's no sense going any further because all the computations would be wrong. Then the step of multiplying through by this denominator is done with this button, and you end up with just the numerator here. On the right-hand side, you get some cancellations and some multiplications. Then you have the collect like terms step, but bring everything over, so everything's on the right-hand side, and collect with respect to x. That gives you the equations where this must be 0 and this constant term must be 0. So those are the equations that you need to solve. This button solves the equations, gives you the values of parameters a and b, and this puts those numbers into the templates and shows you the decomposition. This link takes you to a recorded demo of a similar problem. It's one of the videos that's on the Maple website. An interactive solution from first principles. So here is the rational function. We give it a name. The members of the fractions of the decomposition, give it a name. We look at the difference f minus g. If we simplify this, we get fraction additions over a common denominator. This has to be an identity identically equal to 0. So we pick off the numerator using the numerator option. Collect with respect to x, grab those coefficients. So you see the comma here, this coefficient, that coefficient. That gives the two equations. Maple does not mind that you didn't say equals 0. It assumes that's what you meant. So when you hit it with solve, it puts the equals 0. It solves these equations. It gives you back these two terms. Their equations, and there's an option here we haven't used yet. It's the substitute into. So if we substitute into, we can substitute into here g. Well, I didn't reactivate that, so there's no sense typing that here. But if you substitute back into g, then the return will be the decomposed fraction. For this problem, there's even a coded solution, which is a solution built from Maple commands for those who might want to master the commands. So here is the assignment operator, where we assign the rational function the name f. And the command is a convert to partial fractions. Variable is x. To do it from first principles, write the equation f equals g, simplify, and multiply by the denominator, right? We're picking up the denominator of f, multiply this equation by that denominator, hit it with a simplify. We want the coefficients of the x on each side to match, and the coefficients of x to the 0 to match. So you map the coefficient command onto both sides of the equation. This is x to the power 1, this is x to the power 0. Those are the two equations that you have to solve. Use the solve command. Then you evaluate Q1, which is this equation, using the information in Q5, and you get the decomposition. Or you can use solve identity. This is the approach where you are solving this as an identity in x, that's what that x there stands for, and you're solving for a1 and a2, and it returns the two numbers 2 and 5. Polar coordinates sneaks into the curriculum in the integration section, where you are finding areas in arc lengths of objects described in polar coordinates. So this example is simply the graphing of a limison. This limison, how do you draw its graph without Maple and with Maple? Let's take a look at what Maple's got to offer us here. So here is an animation built with embedded components. So here, embedded components, buttons, boxes for creating these widgets. Okay, so this widget is controlled by this slider, which is the angle in cos theta. And I've written it in degrees because it's easier to understand degrees than it is to understand radians. And so as the degrees go from 0 to 360, you can see the tracing of this limison. This red line, that's the radius vector. But look over here, it's negative. And then it goes positive. And then it goes back negative, and you get that little inner loop. And this gives students all kinds of fits. What are the angles for which you get the inner loop? What are the angles for which you get the outer loop? So this little gadget here is a way for students to understand how to trace the limison 0 to 360. Well, here is a graph of the limison drawn with the plot builder. Here, you can see you can either pick it up from here or down in here. Big plots, plot builder, okay? And it's drawn on polar axes. Now, here we have the graph, and here you see the plot builder with all of the options. If somebody using this worksheet should happen to click this execute all button, right? Execute the entire worksheet, this graph will disappear. And so these are the instructions for how to rebuild this graph if, unfortunately, it disappears. There's another tool for graphing here in Maple, the interactive plot builder. It's an older plot builder. You can access it through a command. It allows you to create a similar graph. This is what the graph would look like. This is the dialog that comes up. You enter the appropriate data and you get this graph. You cannot embed this graph with this older tool, but it does have a little bit more flexibility as far as drawing the figure you want. And finally, there's this table down here that has commands that will draw the graph. If you want to execute these, you would first click on it, right click on it, and you change it to executable math. And you see it goes from gray to blue. And then you could hit evaluate here in the context panel. So you can experiment with these commands to draw those graphs. And a final word is be careful when you convert from polar to Cartesian, because this is r. It's the square root of x squared plus y squared, and that's going to be positive. But the right-hand side can become negative. The appropriate way to convert is to multiply through by that square root and square both sides so that you get an expression that hides that minus sign. This would then correctly draw the limison in Cartesian coordinates. I'd like to take a look at least one section. I've picked this one, the section on polar coordinates. So this is what it would be like. Down here are the examples, and up here are the summaries of the information pertinent to this topic. So remember, the sections summarize information that's contained in a calculus book and add a little bit where the Maple can do more than just the book. So a discussion of polar coordinates, the transformation equations from the polar plane to the xy plane, from the xy plane to the polar plane. And here's the note that Maple has a 2-argument arctan function that puts the angle in one of the 4 quadrants rather than just into one of 2 quadrants. Now, here's a pair of figures that you don't see in a typical calculus book. This is the one you see. You see the grid lines of the polar plane pulled back onto the Cartesian plane. So you have the radial lines and the concentric circles. But those are the inverse images of coordinate lines which are rectangular in an r theta plane. And this affects not only what the student sees in a calculus course, but in vector calculus. To understand a vector calculus course and a vector calculus package, this pair of images is important because you have a representation of a point in polar coordinates on this plane, and then you have it on this plane. So you can think of it as you have a town map. The addresses have on the houses have been changed, or the houses have been moved. A dynamic way to get across this notion of mapping from one plane to the other. Take this curve, which is the cardioid polar coordinate curve drawn in the Cartesian plane. Now, here's an animation. Let's see if we can run this animation here. Why don't we just run it repeatedly? Okay, so here it is being mapped over to the r theta plane. If you look carefully, this is what it looks like in the Cartesian plane, right? This is the cardioid shape that you recognize in the Cartesian plane, and if it gets mapped over to the r theta plane, it will look like this, kind of like a bell on its side. Okay, so the mapping can go both ways, but the ordinary way of looking at this in the applications in calculus here is to draw the polar curve on this grid. But this grid is superimposed on top of a Cartesian grid, but the polar curve also has a life over here in the r theta plane. And here's a figure that you'd never see in a calculus book. This mapping of the Cartesian grid lines over to the polar plane. Okay, so this is what these rectangles, squares, deform to in the Cartesian plane, and this is what the figure in the polar plane deforms to when pulled back onto the Cartesian plane. And a final word, when you're looking at the radius as r equals root of x squared plus y squared, that is going to be a positive quantity. But you have to also make use of this convention that a negative radius shifts the angle by pi. All right, so this is, and we've seen this already, and it's consistent with these trig formulas, the sum formulas for sine and cosine. If this letter y here becomes pi, then sine of x plus pi becomes minus sine. So r equals sine theta, right? And theta shifts by pi, r could go negative by that formula. And same with the cosine if you follow out these two formulas. And here's a brief discussion of what we mean by a curve given polar coordinates. It could start out as an implicit definition with r's and thetas. If you can rearrange it to r equals f of theta, more recognizable. Otherwise, it's implicit. Then the r's are replaced by this square root, and the thetas are replaced by an arctangent, or better yet, an arctangent with two arguments, so you have a more precise location of the angle, quadrant-wise. If it's in the form r equals f of theta, then you would replace the r with that square root, and the theta is replaced by an arctangent, or y over x, or y comma x. Okay, so graphing these kind of curves, you can convert to Cartesian coordinates and apply a tool that graphs implicit functions, or keep it in the explicit form, r equals f of theta, which defines the curve parametrically in Cartesian coordinates via these equations: x equals r cos theta, which is f of theta cos theta, y equals r sine theta, which is f of theta sine theta. So Maple has the tools to do it either way. The simplest way is to leave it in the form r equals f of theta and graph it and say graph the coordinates are polar. This section on polar coordinates also contains this dictionary of polar curves. These are the curves that a student is going to see in all of the examples, integrating, getting areas and arc lengths and all that stuff. It's dynamic. So here you have the limison. If it has cosine or if it has sine, it will orient it one way or the other. And the slider controls the parameter b. So you can see what happens to the limison as you vary the parameter b. Same here. The rows, it has a dynamic representation. As you change the number of petals, or as you move the slider, you will see the number of petals change. Okay, so this table contains the sum total of all the polar curves that a student is going to be asked to work with in a calculus course. There's also a discussion here of the conics in polar coordinates. These appear in calculus books that do motion of the Earth around the sun. Solve that problem. The solution comes out to be the conics in polar coordinates. And if the student has never seen that, here's a quick synopsis of what those formulas look like. And then, as expected, the section concludes with a list of examples, one of which was the one we saw earlier, this limison problem. So there's a selection of problems, exercises, examples that can be perused. Finally, now the question of access. How do you get a copy of the study guide? Well, it's available here at the Maple Web Store, a Maple website here, ebooks and study guides. The alternative that you might pursue is check with your rep, Maple rep. Often there are package deals, bundle, promo, a study guide with a copy of Maple. So this stuff changes all the time. Check into it. This would be one way of pursuing a copy.